Stripping down science. The Naked Scientists.
How do you make a brand new metal? And how does this brand new metal make its way into an aeroplane? This week we're discovering how computer modelling can create new metal mixtures or alloys that have some very exciting new properties.
We'll also be heading off to the laboratory to hear how these newly designed metals are put through their paces.
So what we're looking at now is a box furnace, and what we'd use these for is putting in our samples to give them a heat treatment. And we do this for a long period of time. Right here we've got two more furnaces next to us. They're at 800 and 1,000 degrees centigrade, and they're both on for 1,000 hours.
It's a long time at a very high heat. And in the news, the deep-sea dwelling bacteria that are still eating a meal that dates from the times of the dinosaurs.
Plus how a brain interface device can allow paralysis patients to control robotic arms, giving them the freedom to move again.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
Metal alloys are mixtures of different chemical elements, and adding certain elements can make a metal harder, others can alter the melting point and help the metal resist corrosion. But there are tens of metals to choose from, and how can we work out which to include and in what proportions? Professor Roger Reid is Director of Research at the School of Metallurgy and Materials at Birmingham University. He joins us now. Hello, Roger.
Hello there, how are you tonight?
I'm great. So what's a traditional way of working out how to make an alloy?
Well, traditionally, of course, a lot of so-called bucket chemistry has been used to find out which elements to use for the alloys. So you would typically mix up elements such as nickel and chromium and aluminium and titanium and so on for the so-called nickel-based superalloys, and then you would test them in mechanical testing apparatus and work out whether one has adequate properties for a given application. So, for example, in the jet engine, you may be interested in making sure that the alloys have got sufficient strength or toughness or even something as complicated as creep resistance. So a lot of empirical studies have been done by make-test iterations. You make the alloys, you test them, and then perhaps after maybe a few hundred alloys, you have one which you think you can use.
That sounds like a hideously time-consuming and expensive process.
Well, that's right. You know, many people spend lots of time and, of course, lots of money. You know, it may be up to, for a typical turbine disc for a jet engine, you know, it may be up to £1 million or perhaps even 10 times that to have the alloy ready for use in the engine with all of the necessary test data measured carefully.
So what are you doing which is different?
Well, we've been working on computer modeling programs to try to use theoretical methods to come up with what we think are the optimum compositions for these sorts of components for jet engines. So the idea is that you would do the necessary theory and calculations on the computer and then to choose the alloy composition which you think is best matched to the properties that you need for these applications.
So are you starting off right on the atomic scale with quantum mechanics or doing something slightly different?
Yes. There are different ways to do it. Yes, certainly we make use of quantum mechanical methods, so-called density functional theory, where one, subject to a number of assumptions, solves Schrödinger's equation to work out the bond energies for the different elements, and in particular for the energies associated with the different elements swapping positions on the crystal lattice. So that's certainly something we do. We also use high-level thermodynamical methods based on solution theory, which have got now parameters in there which describe how the bonding behaves.
So essentially you're using quantum mechanics to get figures which you then feed into another larger scale model, which then feed into another one?
We come up with what we call merit indices, and those merit indices are figures of merit which describe how any given trial synthetic composition would behave in creep or in fatigue or in strength. And we do that by making estimates for suitable defect energies which describe how easy it is for that alloy to deform. It comes down to a number of composition-dependent energies, which we can estimate using the theory that you just described.
I guess you're not just dealing with two metals in an alloy, you're dealing with many. Does this add more difficulty?
Yes, that's quite right. The kind of alloys that I look at in my research are the so-called nickel-based superalloys, and those are the alloys which are used at the very hottest parts of the turbine engine of the type that you would use for jet propulsion or for electricity generation in a power generation circuit. And those alloys are quite complicated. They typically have maybe 7, 8, 9, maybe as many as 10 different alloying elements. We add chromium, for example, and cobalt. The chromium is added for much the same reason that you would add chromium to a stainless steel to make it oxidation and corrosion resistant. We add also elements such as aluminium and titanium to promote precipitation strengthening. So that makes the alloy start to behave a bit like a composite. So you have small particles of a second phase present, which adds strength to the materials. And then we add other exotic elements, much rarer and more expensive refractory elements like tungsten, tantalum, and even rhenium, and even some precious metals like ruthenium have been shown to confer the very best properties, particularly in creep, where one is interested in making sure that the alloys don't deform and stretch continuously over time under the stress that they experience in the engine. So yes, there's quite a range of elements which are added, and this does provide the complexity which makes the computer modeling methods useful, because if you think about it, each element needs to have a particular concentration associated with it, and the concentration ranges are quite wide, and with so many elements there, perhaps 8 or 9 or 10, the number of combinations that you can come up with synthetically is quite large. And that's, of course, the power of the computer modeling methods, because we're able to do that sorting and ranking and prediction on the computer without the need to go to the laboratory to make the alloys and do the testing. And that's obviously does two things. It reduces the cost, but it also allows us to identify the compositions quickly. And in a market where you need to get the new alloys into the engine quickly so that new products can be flown within perhaps the period of 1 or 2 years rather than the traditional 8 or 9 years, that's very, very useful.
So are you fine-tuning principles which people have worked out by the rough and ready system, or are you working out new things which can go into the mixture?
Well, new theories have been needed, yes. For certain, of course, we are building on the shoulders of giants, as they say. Lots of people have worked on these sorts of alloys over the last 20, 30 years. And, of course, they can be traced back to Whittle's very first engine, which flew, around about the time of the Second World War. But theory has been needed to explain and to put in place composition dependence theory for the important properties such as I said, strength and creep and toughness. And I think in the last 5 or so years that theory has matured, and that's really what's allowed us to propose these new computer modeling methods to do the alloy design using theoretical methods.
So once you've got one of these, once you run your models, what do you pass on to the guys who've actually got to make the things? Well,
typically we would suggest alloy compositions which we believe to be useful. So that would mean the exact concentration in either a weight percentage or maybe an atomic percentage, a percentage of the different elements there. So, for example, for a turbine disc alloy, we may specify perhaps 15 or 16 weight % of chromium in the latest alloys. You may then have smaller amounts of aluminium and titanium, tungsten, molybdenum, and so on and so on. We specify the compositions which we believe are required to the very best properties.
Brilliant. Thank you very much, Roger. That's Professor Roger Reid from Birmingham University.
And Roger will be with us for the rest of the show, so if you would like to get in touch with any questions or comments,
you can tweet at Naked Scientist, comment at facebook.com/thenakedscientist, or email chris@thenakedscientist.com.
Once we have a recipe for a new metal, how do we find out if it lives up to its initial promise? Dr. Nick Jones from Cambridge University invited me along to the Department of Materials and Metallurgy to find out more about the process, and he also joins us in the studio now. Nick, thank you ever so much for coming in.
Absolute pleasure.
So we've heard from Roger that you get given this sort of recipe. Where do you then start?
Well, as Roger said, they can be either given to me on a bit of paper as weight percents or atomic percents. If they're in atomic percents, then I need to convert them into something a bit more useful for me, which is weight percent. And then I'm into the lab to go to our raw elements cupboard, where we have a whole variety of little pots containing pure elemental metals. And then I start weighing them out, just like you would for baking in a kitchen, only with a little bit of a more accurate set of scales.
How important is it that it's accurate? If you're getting atomic percentages, then presumably your measuring has to be incredibly accurate.
Well, obviously, the more accurate we can be with the measurements, or I make as the measurements before I start making these things any further, the more likely we are to actually be on the composition that's been specified. So if I muck it up at this stage, very much like your cake, it's not going to be what they asked for, at which point someone like Roger gets probably quite annoyed with me and I have to have another go.
And you took me to see some of the equipment that you actually use. So once you've got your measurement, you then need to melt it. And for this, you took me to see an arc melter.
So what we're looking at here is this is an arc melter, and we use this for actually melting up some of our compositions. So we have our raw elements, which we have weighed out, and we place them in one of these little receptacles, so this finger-shaped recess there. And having put them all into that recess, we would put the whole system under vacuum. Oxygen goes into metals very easily, particularly in the hot. We don't really want that. So we'll pump that down to a reasonably high vacuum. And then before we actually start melting these, we backfill the system with argon, which is an inert gas, before striking an arc, which is a bit like welding, and then using that to vary the current, the strength of the arc, to actually melt the elements together. Things mix very well in liquid, much more better than they do when they're solid, so we want to get the thing nice and hot into a liquid form so everything mixes together and we get one uniform solid.
So that was your arc melter, which works in the same way as arc welding. You're actually using a very large electric current that generates lots of heat. So why would you want to do it that way instead of maybe induction, where you set up an electromagnetic field and that encourages the metal itself to get hot, or even a more traditional oven?
I think in many ways, on some of the elements we're trying to melt, we want to get to some quite high temperatures. I mean, Roger mentioned that in some of these nickel-based superalloys that he's designing, there are some refractory metal elements in there, and they have very high melting temperatures. And one thing the arc gives us is the ability to get to these very high temperatures. So we can make small amounts, and these are quite small, about the size of your little finger, the things we make, to try out these materials. Now, if we wanted to make bigger quantities, we might well use a different type of furnace, like an induction furnace, but we may have to melt a couple of those elements together first to get them to a lower temperature, so it's easier to melt them in these other types of furnace.
And do you have any problem whereby if you're passing a current, you are obviously also creating magnetic fields around it? Does that affect the structure that you end up with? I mean, would you get a different structure if you had used a different way of heating it?
I think that these things cool, and that gives us the structures they form. I've never actually personally looked at whether we get an influence of magnetic field. I know some people do look at things in steels where they try and use magnetic fields while the material's at certain temperatures. But in a lot of the alloys certainly I deal with, I don't have magnetic properties, so I get away from that one, so I guess I get off lightly.
So what do you do next? You've obviously melted it, you've allowed it to cool, you have your little test sample. What's the next step?
Well, one of the first things I would do is I'd take a little slice of that material and I would prepare it and then actually go and put it into a scanning electron microscope. And from that I can use a technique of having a very quick check on the composition to see whether I'm actually in the right ballpark. And from there we would actually go and get it sent off to have a more accurate compositional analysis done. If I'm a long way off the composition, like I've just weighed something out wrong because I'm having a bad day, and those happen, then I need to have another go, and there's no point continuing with what could be a quite lengthy process of fully characterising and doing these very long heat treatments as we saw in our introduction. I need to make sure I'm right to start with.
So you've said that these are samples of metal about the size of a finger. If you're then cutting off bits, what sort of size samples are we dealing with?
Well, that can vary, but typically I'd say a few millimetres in length, and if you just imagine taking off the very tip of your finger, it could be something as small as that. The amount of material we can look at can be quite small, actually, and this gives us a representative idea of what might happen with these materials.
You've just mentioned heat treatment, and this was the next thing that you took me along to see, so let's hear a bit of that.
So what we're looking at now is just a box furnace. This happens to be one that goes to 1100 degrees centigrade. They are, as they say, just boxes with heating elements down either side and then ceramic walls all around them. And what we'd use these for is putting in our samples to give them a heat treatment to allow lots of diffusion to occur when they're at higher temperatures. And this makes sure we can assess the crystallographic phases that would form, the different phases. We do this for a long period of time. Right here we've got 2 more furnaces next to us that a colleague of mine is currently using. They're at 800 and 1,000 degrees centigrade, and they're both on for 1,000 hours. So they're quite long heat treatments to allow us to get these materials to equilibrium and make sure we understand what the equilibrium phases are.
Sounds like that could do with oiling, I think. But so what's the point of the heat treatment? What changes would you expect to happen in that 1,000 hours at 1,000 degrees C?
Well, it allows all the elements to move around within the solid. So these things are still solid at these temperatures, and as I said, the elements can diffuse in that material, move around to where they'd like to be, or their lowest energy positions within that solid piece of metal. And as Roger mentioned earlier on, this can actually lead to the formation of precipitates in some case, which, as he said, makes the material behave more like a composite. And we may want to form these because they could, as he said, strengthen the material. So we need to form these precipitates and allow this diffusion to happen. We need to give them the ability to do that, which means high temperature, and then the time to actually do it. It doesn't happen very quickly. Diffusion, particularly of some of the refractory metals, is very slow.
So we're going to end up ultimately with a very different metal compared to when it was first melted. When you've heat treated it for this long, the crystal structures are very different, and so the properties should be different.
Well, that's very much the case. They can be. I mean, sometimes what you get out when you've just cast it isn't quite what you want, and hopefully by giving it these long heat treatments, we get to the equilibrium phase fields, what they naturally want to form. And then if we change some of those temperatures, we can induce these precipitates to form. And therefore, yes, we can start producing a material with very different properties than would have been there in the as-cast material.
And what then do you need to do? So you've already taken an initial sample from the immediate as-cast metal and you know the structure of that. Once you've done the heat treatment, do you need to do the same sorts of tests again?
Absolutely. We need to see what that microstructure now looks like. So this is up from the atomic scale, what actually looks on kind of the microscopic level. We can see quite a lot from how these precipitates, as Roger said, we have to go and have a look at them because the size they adopt, the morphology, so that's the shape, can be quite important. And these things have been designed in, as Roger said, they're actually looking to design these features in. So I need to check whether we've got that right and actually trying to manufacture it. And if we haven't, it's time to have another go again.
But as well as the chemical structure of it, presumably you need to work out if the properties of that metal are the properties that you were looking for. There must be mechanical tests that you need to do.
Well, precisely. We use a range of mechanical tests. This can be from something as simple as a little diamond indenter going in to give us some idea of the hardness. Roger mentioned strength, so we could assess that with a tensile test. We have machines which can do that at higher temperatures to give us some indication of whether the room temperature properties might be good, but is it also going to perform at the higher temperatures that you find in a gas turbine engine? Other things Roger mentioned, he said chromium in there for corrosion protection, and so we might look at oxidation, and these things get very hot. As I said in my piece about the arc melter, oxygen absorbs into the metals, and then we get oxides forming at the surface, and that's bad because it's consuming your component. So we might want to test how good the oxidation resistance of these alloys are, because that's something that's key to their design.
Excellent. Well, thank you ever so much, Nick, and thank you for your tour of the building as well. That's Nick Jones from Cambridge University. And if you'd like to find out more about alloys, about how they're used and how they work, we've made a Naked Scientist scrapbook video to explain it all. And you can find that at thenakedscientist.com/scrapbook.
Distilling the best science. The Naked Scientists. Look us up online at nakedscientists.com.
This is The Naked Scientist with me, Ben Valsler, and with Dave Ansell. And we'll return to our topic of making new metals shortly when we hear how Rolls-Royce take a new alloy and turn it into part of an aeroplane engine. But first, a protein associated with Alzheimer's disease has been seen to cause damage to the blood vessels of the brain, ultimately leading to a leaky blood-brain barrier and an increased risk of neurodegenerative disease. But identifying this mechanism now offers new targets for treating and even preventing the disease. APOE4 is one of 3 common forms of a certain human protein and is a major genetic risk factor for Alzheimer's disease, as well as being associated with poor recovery from brain injury. Now, research published in the journal Nature shows that APOE4 activates a pro-inflammatory pathway in pericytes. These are cells that are found in the walls of brain capillaries, and they're responsible for regulating blood flow and controlling the blood-brain barrier. When this pathway is activated, it leads to an increased uptake of toxins in the brain. It essentially introduces a leak into the blood-brain barrier. Now, the blood-brain barrier plays an essential role in allowing nutrients in and keeping toxins out of the brain, and so dysfunction of this barrier can lead to damage and ultimately neurodegenerative disease, including the build-up of plaques that are characteristic of Alzheimer's. Robert Bell from the University of Rochester in New York and his colleagues targeted a particular component of this pathway, cyclophilin A, and this is a protein which is inhibited by the other forms of APOE, so the healthier forms, and it's also known to be involved in blood vessel damage elsewhere in the body. It's implicated in heart disease as well as in Alzheimer's. Mice carrying the APOE4 gene express 5 times more cyclophilin A than those carrying the other versions of the gene, so it's obviously a very good target. And in fact, when it was blocked in mice, either genetically or by using an immune suppressant drug called cyclosporine, this reversed the damage and it dramatically cut the leakiness of brain vessels. Now, this offers a very good target for treating or preventing the damage that will ultimately lead to Alzheimer's, and Alzheimer's, as it's the most common form of dementia in older adults, is certainly something we need to look at.
Sounds very hopeful. Now, a method for doing microscopic origami has been developed. There are more and more applications for very small three-dimensional structures, ranging from new materials, batteries, to aerials. But whilst we're very good at making minute two-dimensional structures, the third dimension is much more difficult. The Japanese, of course, developed ways of converting 2D structures to beautiful 3D ones, origami, and more recently mathematicians have formalised this process to work out exactly what you have to do to make a certain shape. But folding structures on the micrometer scale is still rather fiddly. There have been some approaches involving using liquids drying out to pull things up, but they're all quite complicated or fairly limited. However, Jenny Ryu at the University of Colorado have come up with a very neat solution. They developed a process which involves taking a sheet of polymer, so just a bit of plastic, stretching it in one direction, and then exposing it to ultraviolet light in certain areas. And this ultraviolet light kind of causes it to flow plastically a bit, and so the top surface is now happy being the size it is when it's stretched. And then unstretch it and do the same in other directions, so you have lots of areas which are kind of bigger on the top than they are at the bottom. This means if you then cut out your shape, it's already got all the stresses in it which make it just fold up into a nice structure immediately. They can change the angle the polymer folds to by changing how much exposure of ultraviolet light they put onto it. And so far they've folded up a box which is about 10 millimetres across, which isn't quite the same as a microscopic thing, but they've built computer models which show how this works, and it should go down right onto the micrometer scale, leaving all sorts of different ways in which it can be used.
UV light does have a tendency to damage polymers, though, doesn't it? So are we ending up with 3D structures that are incredibly detailed but ultimately a bit more fragile than they would have been if we did use a different technique?
They've essentially designed the polymer with areas to absorb the ultraviolet light. So it is changing the polymer, but it's in a way in which they've designed it to. So I doubt it's going to be doing serious damage to it. Anyway, you're only exposing it to a few minutes. You're not leaving it outside in the sun for a year.
And then these polymers, you then presumably attach the active things that you want to the existing 3D structure because you don't want to expose those to intense UV.
It depends what you're doing. I mean, if you're making an aerial or something, you'd probably put the copper on the bottom already and you make everything flat and you'd expose it to the UV and it would then all fold up nicely and you'd have a nice three-dimensional aerial. Whereas with some things you might want to expose it, like cover it later.
Now, imagine not being able to just pick up a glass and have a drink, and instead having to rely on others to help with this most simple of tasks. This week, a brain interface device has allowed a paralysed stroke victim to drink for herself for the first time in 14 years by controlling a robotic arm just using her mind. Professor John Donoghue from Brown University reports on this work in the journal Nature this week, and he joins us now. John, thank you ever so much for joining us.
Well, thank you. I'm pleased to be here.
So what did you set out to show with this piece of work?
Well, previously in 2006, we had shown in spinal cord injured patients that they were able to control a cursor on a computer and type or play a video game, but we didn't know whether people with paralysis like these two people with stroke that we studied, would be able to control something as complicated as a robot arm. And this was very important because in order to be able to do things for yourself, you have to be able to reach out and grab something, your drink or your morning toast. Otherwise, you're completely dependent on other people. So our test was to see whether people were able to control something this complex.
So what is the increase in complexity from controlling a cursor on a screen through to controlling a robot arm? Is it the extra dimension, the fact that you're working in 3 dimensions instead of just 2?
Well, it's even more than that, because if you want to grab onto something, you have to open and close your hand, and you have to do it whenever you want. So the challenge was to ask this tiny population of cells that we were picking up in the brain to not only be able to move in 3 dimensions, that is, put your hand anywhere you want in space, but also to be able to open and close your hand whenever you wanted.
And how does the implant technology actually work?
We put a tiny sensor about the size of a small pill on the surface of the brain, and it has 100 hair-thin electrodes that go just into the surface, and they pick up these very weak impulses that come out of neurons. And the impulses are taken out and transformed into a command signal. So it's a pattern of brain activity that becomes a command signal to run the robot arm.
So it's a computer science problem as well as a neuroscience problem and a technology problem, because you need to interpret what's going on in the brain in order to tell that into a reliable signal.
Actually, yes. This is a wonderful example of how it's necessary for engineers and clinicians and neuroscientists and computer scientists all to work together in a team to solve the problem of picking up brain signals, transforming them into meaningful control signals, running them through a computer, and roboticists, of course. We've worked with roboticists to be able to take that command signal and actually make the robot arm do what the person is thinking.
I understand that one of your patients had actually had this implant for quite a long time, and one of the things that people have been worried about with this sort of work is that the implants would either generate some sort of response, perhaps a local inflammatory response, or they would just fur up, or they would break and stop being useful over time. This seems to be a really good demonstration that actually these things have longevity.
Well, this is very encouraging that an implant in the brain can last a long time, but we have to be very cautious. It's only one person. So far, we've had several others that we've studied for nearly a year, but we're concerned that the materials may break down, and we began to see certainly evidence of that as one of the problems.
In particular, your patients have had a brainstem stroke, so they are essentially isolated from their own body. Do you think that the same techniques could work with people suffering from other forms of paralysis, perhaps spinal injury or stroke in another region of the brain?
Basically, what a stroke like this does in the brainstem is it disconnects the wires or the fiber pathway that goes from the brain to the spinal cord and then ultimately out to the body. So for any person who has an intact and functioning brain, this technology could potentially work. So there are millions of people with various forms of paralysis, spinal cord injury, stroke in other areas other than the brainstem, and a disease like ALS or Lou Gehrig's disease, in which the connections from the spinal cord to the muscles die, and then again break the pathway from thinking about movement to actually making the movement or disconnecting the brain and the body.
And could we use other parts of the brain as well? So could we actually have multiple systems running at once, one to control a robotic arm and then perhaps another one to control a wheelchair, for example?
Could be, just like we have parts of our brain that control our legs and our arms. Of course, it all is coordinated together, and we can't run too many things at once or we might get into trouble. But it's very encouraging as we learn more and more about how the brain turns thoughts into actions. We know there are very large networks and many areas involved, and all of those are potential candidates. We could tap into the earlier parts of the stream to get additional arm signals, or we could go to the leg area, for example, perhaps to control a wheelchair, or even exoskeletons on the legs of a paralyzed person to make their legs move so they could walk.
And it's obviously wonderful to be able to control a robotic arm, but we have seen other work where they've been using a special type of electronic stimulation to actually make muscles move. Could ultimately this be used to bridge the stroke site, bridge the gap, and reconnect muscles to what the brain is thinking? Could we get people controlling their own limbs again?
Yes, that's something that we're working on very much. We're very interested in reanimating the muscles. And this is work of Hunter Peckham and Bob Kirsch at Case Western, where they've implanted stimulators in the body And it leads to wires that go to the muscles or to the nerves. And when that stimulator goes off, the arm contracts. And there are about 600 people that they've implanted that are standing up or moving their arm to some extent as a consequence of this wonderful technology. So we're working with them to try to say, instead of controlling it with an outside switch, so the current people will use a button that someone can push or a switch on their shoulder. If they can wiggle their shoulder, they can make their hand open and close. But now imagine we could connect BrainGate, this brain sensor, take the brain signals and wire them back into the stimulator, which then goes to the muscles. So we sort of have a physical repair for a broken biological system.
Well, it's a fantastically exciting work, and it looks like it's going to come on leaps and bounds. Already it's changing at a phenomenal rate. So thank you ever so much for joining us. That was Professor John Donoghue from Brown University. And as I said, you can find his work in the journal Nature this week. And also this week, a community of microbes has been found living alive in 86 million year old deep sea clay. Although, I say alive, but they're not exactly thriving. They seem to be surviving at the bare minimum energy requirement needed to qualify as being alive. Now, along with colleagues in Germany and in the USA, Hans Roy from Aarhus University in Denmark collected very long cylinders of mud, known as sediment cores, from deep under the Pacific Ocean seabed during a cruise of the current system known as the North Pacific Gyre. Writing in the journal Science, the team measured oxygen and carbon concentrations at different depths. They then measured the numbers of microbial cells. At the surface, they found 10 to the 8, that's 100 million cells per cubic centimetre of mud, but by 20 metres below the surface, which is in sediments laid down over 66 million years ago, they were finding just 1,000 cells per centimetre cubed. Further down, the cells were actually so sparsely distributed as to be uncountable using the techniques they were using, but evidence of their presence was still seen in oxygen consumption. The oxygen consumption rate did eventually sort of bottom out and reached a stable minimum, and the deepest microorganisms were consuming 3 orders of magnitude less oxygen than the same sorts of cells would in culture on the surface. And that incredibly low respiration rate suggests that they are existing in a sort of long-term stationary state, almost in suspended animation, subsisting on the bare minimum oxygen to survive, and that means they're unlikely to be growing or dividing. Our present understanding of microorganism respiration is built mainly on our experience of culturing fast-growing microbes at the surface. For obvious reasons, the microbes that have been interesting to us are things like the ones that infect us or affect our food chains and so on. So it's probably no surprise that what we discover deep under the seabed doesn't actually match with our expectations. And that's even less of a surprise when you think that this layer of sediment has seen no new food, no new carbon going in since the dinosaurs were walking on the surface.
That's incredible. These are definitely cells which are living off oxygen, because there are a lot of bacteria and things which could live off other forms of energy.
Because of the fact that these cores are actually oxic, there is oxygen there, they are looking at the consumption of oxygen and the turnover of carbon products. So there may be other species there that are anoxic, that are feeding on different types of cycle, and we certainly know that there are species of bacteria that can cope with no oxygen. But these in particular are looking at bacteria that respire oxygen, and this incredible slow life that they're having, given that they were probably buried, or certainly their ancestors were buried, something like 86 million years ago.
And now for a roundup of other science stories hitting the headlines this week, here's Mira Senthilingam.
Large city hospitals act as breeding grounds for the highly resistant bacterium MRSA and facilitate its spread to more regional locations. A study led by Ross Fitzgerald from the University of Edinburgh sequenced the DNA of 87 samples of methicillin-resistant Staphylococcus aureus, or MRSA, from patients in over 15 hospitals across the UK. The team deciphered the genetic makeup of the bacterial samples to trace the origins of infection found in more local settings, and found that hospitals in big cities act as a hub for transmission of MRSA between patients.
You don't have to actually have a disease to be infected with MRSAs, but they can carry the MRSA with them to those regional hospitals. We might be able to identify patients who become colonized when they're in these city hospitals. And if we can screen them, identify patients who are MRSA carriers, we could then treat them using kind of topical antibiotics to decolonize or remove those MRSA so they're not then spreading them back to those regional centers.
The cellular mechanisms underlying the onset of tinnitus have been discovered by scientists at the University of Leicester, publishing in the journal Hearing Research. Working with nerve cells from the brain's dorsal cochlear nucleus, where signals are relayed from the ear to be decoded by the brain, Martin Hamann found that on exposure to loud sounds, the erratic signalling in these cells, known to result in the ringing or buzzing associated with the condition, are caused by malfunctions in potassium channels within the nerve. The work leads the way for potential drugs to restore the functioning of these channels, enabling the nerves to return to their normal state.
You can have a variety of tinnitus. It can be on one ear or on two ears. It can be different frequencies, so the perception can actually be altered differently. It can occur a different day of the time. So it's very difficult to pinpoint the mechanism, considering it is quite diverse. So finding something that is actually so specific can be quite promising in finding a specific therapeutic target.
The Earth and Moon were bombarded with asteroids nearly 4 billion years ago, reshaping their surfaces in the process. It's known that both our planet and the Moon were bombarded with objects thought to be either asteroids, comets or protoplanets approximately 3.9 billion years ago. Now, writing in Science, David Kring from the University Space Research Association in Texas analysed samples of moon rock from the Apollo 16 mission, which contained 30 surviving fragments of the colliding objects, and identified the culprit of the collisions to be asteroids, providing greater insight into our early solar system.
This is a period of bombardment that immediately precedes the earliest isotopic evidence of life on the Earth. And so we're constantly trying to address, could this bombardment have something to do with the origin and early evolution of life? To the extent that we can tease apart more details of the objects hitting, the pace at which they hit the Earth and the Moon, and what it is they delivered to the Earth and the Moon will better help us evaluate those questions.
And finally, the precise way in which plants pollinate has been uncovered by scientists at Brown University in the US. During pollination, hundreds of pollen containing sperm stick to the stigma of plants such as Arabidopsis and create tubes through which they deliver the sperm to the plant's ovules. Precisely 2 sperm are delivered per ovule, as any extra can result in poor seed development. But the way this is controlled was previously unknown. Working with models of Arabidopsis in the lab, Mark Johnson and colleagues found that the plants generate a signal when sperm have successfully passed down the tubes to fuse with the egg inside the ovule, as the signal prevents any further pollen from landing.
Plant fertilization process waits until the moment when fertilization has been secured to prevent multiple pollen tubes from coming. So in the case where defective sperm are delivered, that ovule continues to attract more pollen tubes. So if we can understand the molecular mechanisms that are the basis of these systems, we can then improve the systems, or perhaps we can engineer them to be more robust and be able to resist adverse environmental conditions.
And that work was published in the journal Current Biology.
That was Mira Senthilingam with our Naked Scientist Newsflash. You can find the transcripts and references for all our news this week on our website at nakedscientist.com/news.
Thank you, Dave. Now, with summer apparently on its way, scientists who study snow are obviously having to find ingenious new ways of studying what happens, and in particular looking at the physics of avalanches when snow cascades down a slope at up to 100 miles an hour. Luckily, they don't have to find a nice snowy mountain in which to do it. Natalie Vriend at the University of Cambridge's Centre for Mathematical Sciences simulates avalanches by using what looks like a big metal phone box leaning on its side. There are no glass walls to it, it's just a rectangular frame and a narrow conveyor belt on a slope. Planet Earth podcast presenter Sue Nelson went to see Natalie's experiment for herself and discovered something very familiar sliding down that slope, but rather than beautiful white snow, it was sand.
Both snow and sand are consisting of small particles. And these particles, when they start to move, they interact and collide with each other. And because of that, the physical processes that occur on this small scale are actually very similar. So we're doing our experiments with sand instead of snow.
Okay, well, can you demonstrate to me what you actually do? Can we turn this huge contraption, this conveyor belt of sand on?
Yes, of course, I'm happy to. I'm opening a valve that opens the sand flow. The sand is being let in at the top of the incline. The distance where the sand can avalanche is about 3 meters long. So we bring in sand at the top, and it starts to avalanche down.
Oh, yes, I can see now some of the sand coming out of a little tube at the top of the slope, which is just a bit higher than me, so it's a couple of meters high.
At this moment, the sand is not flowing very fast. What we can do is actually open the valve a little bit higher, so that the sand starts to come out in bigger quantities.
Oh, gosh, it looks like that's really interesting. It looks like your slope of sand, the central bit, now looks like a sort of flowing molten river of sand.
Indeed. And if you look very carefully, you can see that the middle part is flowing very fast, but there's bits on the side, like dikes.
Yes, that's sort of turning round and not moving so much.
Exactly. And they're actually sand grains that are static.
And is that what happens when snow goes down a slope?
Yes, indeed. When a mass comes down a mountain, it goes the fastest in the middle, and the velocity goes further to zero towards the side. And therefore, if you look very carefully at deposits in the mountain, you can always see that the snow kind of carved its way through a deposit and left debris on the side.
How did you choose the angle of your slope?
The angle that avalanches usually occur is between 30 and 45 degrees. And that's actually pretty steep. It's much steeper than you would ever drive on. Let me change the flow rate right now, because then you can see some other features as well. Okay, what you see now,
that's interesting. Instead of a free-flowing river, it was almost like a drop of treacle.
So in this case, because we reduced the flow rate, there's not enough sand coming through to form this continuous river. Because of that, the sand accumulates at the top of the incline and just starts to avalanche. The slope fails when there's a certain amount of sand available. So you get these intermittent avalanches, and they almost look like tongues going down the incline.
What do you hope to learn by studying this flow, this avalanche of sand? Because a certain amount is known already.
It is really difficult to understand exactly what's going on, because if you can imagine, if you have a flow of water down an incline, researchers know pretty good how to investigate water down an incline. If you have a solid material, the physical laws are very well understood as well. In this case, you have this odd mixture of different phases. As you look in the middle of the river of sand, it looks like a flowing stream, and it goes very fast, and there's a lot of motion going on. But if you look at the side of the river, it's static, and that's really hard to model. So the bigger picture is that we want to understand where the avalanches are going, how far they get, and how forceful and how big they are, what kind of pressures occur in them. The reason is that we want to understand where we can build buildings and roads and where it's safe for people to live. In the past, people relied on historical records, but they may not be very accurate anymore because the climate is changing. And the second reason is that not at every point in the world we have historical records. So we want to be able to model snow avalanches from a physical point of view to actually be able to apply to every valley and every mountainside in the world.
Natalie Vriend from Cambridge University. And you can hear a longer version of that interview with Sue Nelson on the Planet Earth podcast. Find that on our website at thenakedscientist.com/Planet Earth.
Laying the facts bare. The Naked Scientists.
This is The Naked Scientists with Dave Ansell and with me, Ben Valsler. And now we return to our topic of making new metals to find out how a novel alloy makes the leap from academia to aeroplane. In pursuit of better efficiency, jet engine manufacturers like Rolls-Royce are constantly searching for materials that will enable their engines to run at higher temperatures, more quietly, and give out more power. I met Dave Rugg, material specialist for Rolls-Royce, under an enormous Trent jet engine to find out what happens once a new material is made.
The first thing that we have to consider is what we're actually going to use the material for. And the key things there really are the load regimes that it's going to be subject to. So is it going to be high temperatures, it's going to be high fatigue loading, and also how we would actually go about manufacturing it in a cost-effective way, or indeed if it's manufacturable at all at real length scales.
So what sorts of properties are you looking for? Say if you need to make a turbine blade, what do you need that metal to do?
There's a very wide range of loads that the materials are subject to. For turbine blades, obviously one of the key things is how the material behaves at very high temperatures. So there we'd be looking at creep behaviour, which is basically the material stretching under load at high temperatures. But also there's a lot of other loading that the material is subject to. So that can be things like fatigue loading because of the centrifugally induced stress, but also gas loads because the blade's having to do a lot of work or extract a lot of work from the airflow.
Now, we are next to a Rolls-Royce Trent engine. How many different materials go into making something like that?
We've got hundreds of different materials and product forms that go into an engine. In terms of the main alloys, we're probably in the order of low tens, but lots of different product forms that all have different mechanical properties associated with them.
And once you've got a material, it presumably then needs forming into the right shape and testing it in a whole different way to just testing the material on its own. Does that introduce new hurdles, new problems?
Absolutely, and it's a key area and really the most important part of the materials organisation within the company, because the material behaviour in component form can actually be impossible to predict from specimen behaviour. So what we have to try and do in the material introduction process is to try and minimise our costs associated with specimen testing, but give ourselves a high level of confidence that when we do component tests, they're going to be successful.
Presumably also all of the ways of tooling, all of the actual manufacture techniques also need to fit with the properties of the material.
Absolutely, and you find with quite a lot of materials we have to actually use tailored manufacturing routes, and there can be as much work associated with coming up with optimised manufacturing methods as there can be with the alloy design itself.
So once you actually have something, it's gone through all of your tests, what's the process then to make sure it gets into the next generation of engine?
The key thing there is the engine development project, and the chief engineer there will undoubtedly have a very big task on his hands or her hands in terms of meeting the efficiency and performance targets. And quite often materials are integral to being able to produce that improvement. So the chief engineer might be looking for design improvements, and in order to do that they might need materials that operate at higher temperatures, higher stresses. If there's a window there in the engine that the material will give specific gain, then the chief engineer potentially will be interested in picking up a new material. What then happens is that the engine development program would actually use components made of the new material, and through the development program they'll be subject to loads and temperatures that are well outside anything the material would normally see in commercial operation.
And how much of a gamble is there on the fact that you'll get the materials that you want? These things are years, even decades in development. So when you've set a challenge for the universities to provide a material that meets certain goals, can you then set about designing an engine trusting that you'll get it?
That's an extremely good and rather difficult question, and to answer it I would say it's probably easier to look backwards in time rather than forwards. And if you'd asked me 20 years ago if we would have new titanium alloys that we'd be using in the engines, I'd have said it's going to be very difficult because they're already very well evolved and pretty much optimised. But of course history would have proved me wrong. We've got a lot of advantages now in terms of modelling and understanding the physical mechanisms behind material behaviour that are actually giving us new insights into the way that materials work, and therefore much more scope for producing really tailored alloys by understanding the physics rather than just doing the evolution empirically.
Do you ever get a huge breakthrough that you didn't expect and have to sort of go back to the drawing board?
Absolutely, and I think some of the relatively modern materials in terms of intermetallics as an example, where the materials are somewhere between a metallic and a ceramic in terms of their behaviour, that's been quite a big surprise, I guess, for the industry over about the last 20 years, although trying to make those work in a real engineering sense is quite difficult because you pay for the benefit one way or another. So in the case of intermetallics, that's by way of them being rather brittle, which has its own challenges in both manufacture and in use.
How do you go about saying to universities, this is what we want and this is when we want it?
Well, there's a few key things that drop out of that, and some of them aren't particularly intuitive. One of the prime examples would be that in terms of understanding current product, there's a huge amount of research going on at the moment with well-established alloys that give us a much better insight into the actual physics of how the materials work, and then that gives you the opportunity to actually develop new materials from that. But we do also have a variety of different means by which we can feed that information and those targets into the universities, so that we set challenges basically to the academics and say, in 10 years' time, we would really like an alloy that's got an extra 10 degrees C temperature capability, which may not sound like much, but is an incredible differential in terms of the product, or an extra X% of fatigue strength.
So it's not just the metallurgists and the material scientists, but the physicists as well that you are getting on side?
Absolutely. There's some key work going on there in terms of both atomistic modelling, molecular dynamics, crystal plasticity modelling that's actually informing the alloy development process. There's some materials being developed now, and in fact I've actually seen service already that essentially have been developed on the computer rather than in the foundry, which is quite remarkable.
And we've been talking as if the jet engine is the final product of a long chain, but if you're developing new and interesting physics, you're increasing the understanding of the materials, that must also feed back into the academic community. So not only do we get new, better, more efficient, more powerful engines, but we also get a better understanding of the world around us.
Absolutely. And materials are a great system to work on. Metallic materials, as an example, actually behave like composite materials, and you can learn a great deal about the way that physics actually works by studying real things in real environments.
Dave Rugg, materials specialist at Rolls-Royce. This is The Naked Scientists. This week we're talking about making new metals. We're joined by Nick Jones from Cambridge University and Roger Reid from Birmingham University. We've had a few questions in. I think quite a nice one to start with. Nick, let's hear your opinion first. Cedric Merriman in Second Life has asked if rare earth metals get used in alloys, and he said that given their high price, he'd assume not. So what are rare earth elements, and do we use them?
Well, rare earth elements are just a certain part of the periodic table, which is a group of elements, and some of them, such as yttrium and lanthanum, do find some small percentage uses in some modern alloys, but as you say, there's no large-scale use of them just due to their high cost.
Roger, when you're designing new alloys or when you're modelling them, do you work around the cost? Are there ways that you can replace things that rare earth elements would otherwise do?
Yes, it's certainly true that we consider the cost. Certain elements like rhenium, for example, in turbine blade alloys are now very expensive, several £1,000s per kilogram. And when one's interested in building a jet engine with perhaps 100 blades per row, then the cost can become quite significant quite quickly. So certainly there are calculations done to trade off the relative benefits of elements like rhenium and tungsten and molybdenum and other refractory metals against their disadvantages, which of course are their cost and also their scarcity.
Thank you very much. Android Neox, also listening to us in Second Life, is asking about the heat treatments that we do. And he said, when we're talking about diffusion in the metal, do we mean that the metal is melting and then diffusing as it would in a liquid, or is there a different process going on? Does it stay solid and just the atoms move through it?
We're absolutely talking about it still being in the solid, and the atoms do move through them, and there are processes that occur. That's why you say they mix better in a liquid state, because things can move more easily than when they're forcing their way through a solid lattice. But that's why I said we have to give them time and temperature. The temperature helps them getting going, it makes them moving a little bit easier, and the time just to allow them to move the distances. But yes, they are moving through the solid state.
And Roger, when you're designing a new metal, again, obviously you have to take into account the sorts of heat treatments it's likely to go through. How do you model that into it as well?
Well, again, there are thermodynamic databases available for estimation of the melting temperatures and the heat treatment temperature windows that are available. Those, of course, are based on thermodynamic potentials which have been estimated and put into computer-based models. Most of the time, those models are accurate and can be used to estimate whether any given alloy has an appropriate heat treatment window to allow that to happen without the melting occurring. Interestingly, for the turbine blade alloys, they will have to be heat treated at temperatures really quite close to the melting temperature, but obviously lower than it so that the turbine blade won't start to melt incipiently during the heat treatment process.
And a slightly different question from Drea Swat. What materials does a car consist of? I guess what sort of metals are in there?
Well, we've talked quite a lot tonight about some quite high-performance alloys. So, we've talked a lot about nickel-based superalloys, and these are quite expensive materials. Cars want to be a bit cheaper. We want to be able to afford them from our own pocket. So we quite often use more common alloys such as the steel, so iron-based alloys, or aluminium alloys, which are a little bit cheaper due to their cheaper raw materials.
And now, with a very attractive question, here's Hannah Critchlow.
The Naked Scientist's Question of the Week, brought to you in association with the Houter Wisman Foundation, supporting science and education from Alpha to Omega.
Here we apply some naked science force to this week's question.
Hi, my name is Mark Andrew and I'm a photographer in Sheffield. My question is it possible to create a magnet so powerful that it crushes the object it attracts? For example, can you make a fridge magnet that would cause a fridge to collapse?
So, can we make a magnet so strong that it squashes, rather than sticks to, your white goods? We asked Joe Brown, who works at Oxford Instruments. Here he designs superconducting magnets that are used in the research labs and clinic, and he wrote in to let us know.
Some of the work I do involves calculating the forces of attraction between the magnet and any magnetic materials in the environment. This means that the question, can we make a magnet so strong that it will crush the object it attracts, is of particular interest to me. Magnetic materials in the general sense are those known as ferromagnets, the most common example of which is iron found in the steel that makes up many objects in our everyday lives. When positioning our superconducting magnets in laboratories, which often contain large quantities of steel in the building framework, laboratory furniture and experimental equipment, we have to perform calculation of forces between the magnet and this local environment. These calculations show that for any magnet which we can conceive of today, the simple answer to the question is no. The magnetic forces are insufficient to crush any object it attracts. This is not to say that the forces involved are small, and it is quite possible to have situations where a loose metal object, such as a steel waste bin, can be accidentally attracted and firmly stuck to the outside of a magnet system. In such circumstances, the bin will come off worse in the encounter, ending up severely bent. To help prevent such accidents, large magnets, such as those used in MRI scanners, are magnetically shielded, using special configurations of the windings making up the magnet, reducing the magnetic field around it. Special consideration is also made to the position and surroundings of the magnet, and you will not find objects like steel waste bins within an MRI suite.
So it appears you might be able to make a magnet strong enough to get your white goods flying across a room and denting on impact, but it is unlikely that you'd be able to produce enough magnetic force to completely crush your fridge. And moving on to our next question.
Dear Naked Scientist, my name is Edward Draper. All along the major roads of the UK, you can see little white flowers appearing. And if you stop and look, you can see that it's a form of scurvy grass. Now, this is a beech plant, and it's found a successful niche of the first few inches from the roads. Given how widespread this flower is, how did it get there?
So how do species infiltrate the verges of our UK road systems, and do motorways create a microclimate? Send your thoughts to Chris at thenakedscientists.com, tweet at Naked Scientists, write on our Facebook page, or join in the debate on our forum, which is at nakedscientists.com/forum.
That was Hannah Critchlow.
And that's all we have time for this week, barring this one last question from Berrigan Betts in Second Life. He wants to know if you can extract hemoglobin from blood like Magneto does in the X-Men. Sadly, not, because it's not actually the ferromagnetic version of iron. Next week, we're attending the Chelsea Flower Show to find out how fungi help plants grow to their full potential, and we'll explore the role of microorganisms in keeping the world well fed. Thanks very much to our production team of Mira Senthalingam, Tom Simpkins and Louise Anthony, and the email address for any questions is chris@thenakedscientists.com. Thanks for listening.
The Naked Scientists podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the STFC, the Natural Environment Research Council, and UK FAST. For more cutting-edge science, join us online at nakedscientists.com.